Welcome to another lesson. This lesson is a Unit 1 lesson, right? Under the section, on the Module 2 section of your syllabus, right? We are going to talk about waves on a whole and some of the characteristics of a wave, right? When we talk about waves, you're going to see that the two general things that we know that a wave can do or should be able to can do is to go through a process of reflection and refraction. But there are other things that this lesson will be about. It will not only be based on these two things, it will be based on other things as we go along. So just follow along with me. As we know, reflection speaks to the the bouncing back of a wave when it meets a boundary. As you can see here, this is a typical way of looking at reflection. Whenever reflection occurs, right, the angle of incident is equal to the angle of reflection. Now remember, when a light ray is going towards a boundary, it's going to be at an angle to the normal. This broken line right here is going to be the normal, right? It's just an imaginary line. And with that now, the ray that is going towards the or the wave that is going towards the boundary is called an incident wave, and the one that is coming, that is bounced back, right, that is going to be a reflected wave. Now there are different types of reflection. This one clearly shows you that it's a complete opposite, right, in terms of what is happening here. But there are times when you can use a curved boundary to reflect a wave. But whenever we reflect it, we realize that the boundary or the reflected wave takes the shape of the boundary. So that's something to point out whenever we're talking about reflection. Now, refraction now is another characteristic of a wave. It means that any wave or any wave on a whole should be able to can go through refraction. Refraction, as you would imagine from fifth form level, the speaks to the changing of the speed of the wave as it passes from one medium to the next medium, right? So in essence, it's the bending of light rays mainly, or not only light rays but waves on a whole. That's what refraction is. Now reflection is the bouncing back, right? But now refraction is now the bending of light rays. And when it bends the light ray, it's passing through different mediums. It's going to bend it. And what is essentially is happening is that the speed of the wave is now changing. Now, as you can see from this diagram, we have a wave in a deep medium or a deep region. That's pretty much like almost like a deep water scenario. And there's a point now where there's a shallow water, right, at a particular boundary. Now, if this wave is coming in at an angle to the boundary, what you will see is that one part of the wave is going to go across the boundary, go across the shallow boundary before this end, basically. So what you will see essentially is that the speed at this end is going to be different from the speed at this end, because obviously this portion of the wave is now in the shallow region. So that will result in a change in the speed. Similarly, because this part of the wave is in the incident medium just the same, it has not changed its medium, then the speed is going to be different on this side of the wave. So that is what is really happening as the wave progresses throughout different mediums. Now, with all of this being said right here, we can come up with a simple equation to just show that the angle of incident, right? The angle of incident has some relationship to do with the speed of the wave in the shallow region and so forth, right? So using geometry, we could come to the understanding that sine theta 1, which is the angle of incident, divided by sine theta 2 is equal, and sine theta 2 is the angle of refraction, is equal to v1, which is the speed of the wave in the shallow, in the deep region, right? Divided by the speed of the wave um, in the shallow region, basically, right? So having this information, we could use this, providing that we know the angle of incidence and the angle of refraction. We could use this to ultimately find out the speed of the wave when it enters into a different medium, right? So we could use this information that says sine theta 1 is equal to v1 divided by sine theta 2 is equal to v2. And it's easy to remember. Just remember that everything is on the same level. So sine theta 1 corresponds to v1, sine theta 2 corresponds to v2. All right, just remember it from that standpoint, because it's an equation that can be used, or we're going to use it further on to derive something else, right? So that's just refraction on a whole right here. This is a simple question that you can go and look through, right? Because it's already worked out here, but you can do it for yourself to just see what is happening. But essentially, what we're trying to find here is the angle of refraction, right? That is made at the boundary, which is Q2. So in a sense that we're trying to make Q2 become the subject. We know Q1 already, which is the angle of incidence, is 35 degrees. So we're saying now sine of 35 divided by sine theta 2 is equal to the speed of the wave in the incident medium divided by the speed of the wave in the refracted medium. So put in all that information. Then we need to transpose to make sine theta become the subject, right? When that happens, now we get all of this number right here, right? We make sine theta 2 become the subject. Then we want theta 2, which is the angle of refraction. Then you would have to find the sine inverse to get rid of the sine. So the opposite of sine in a number is finding the sine inverse. So you have to sine inverse both sides. Sine and sine inverse cancels out, leaving you with sine inverse of 0.7302. And if you do that, then you can find out that theta 2 is now 47 degrees, which is the angle of refraction. Now, another type of characteristics here that we should make mention of is the whole process of diffraction, right? Now, diffraction is the process of spreading out a light, or well, not light by itself, but spreading out waves, right? As it passes through a gap. Right? So it's not as easy as we might think, right? It's not as easy as we might think. In order for us to observe, great diffraction taking place, the gap, the size of the gap, has to be the same as the wavelength of the wave. All right. If the gap is larger than the wavelength of the wave, then it means that the wave are going to pass through, um, with little to no effect of diffraction taking place, right? If the gap is too small, then what you would observe is that the waves will be reflected back, right? But whenever the wavelength, right, which we know wavelength is lambda, whenever lambda is pretty much the same length as the gap, then what you would see is that the waves are going to spread out in a circular pattern and so forth. So that's what we call diffraction. So mind you, if you want to find the wavelength, all you're doing is measuring crest to crest, because these thick lines right here is basically crest, right? So this is one crest, this is another crest. By measuring the wavelength between two crests, you get, or by measuring the distance between two crests, you get a wavelength. If that wavelength matches the width of the gap, then obviously perfect diffraction is going to take place. All right. Now another characteristics we should talk about. Now all waves, right, should be able to can go through this process of interference. Now interference is, as the name suggests, it's when things come together. You understand? Whenever we're dealing with waves, It is that process where we algebraically, right, find the resultant wave using a process of what we call, you know, the process of, or the principle rather, of superpositions of a wave. Now, superpositions of a wave is simply when you have, more than one wave on a graph. When that happens, depending on how the waves are positioned, then it can actually create a much larger resultant wave, right? Now, this happens here. So there are two types of interference, right? There's what we call constructive interference, and then we have what we call destructive interference. Now, this graph right here is showing constructive interference. Constructive interference occurs when both waves are in phase with each other, meaning that they start at the same position. There's not a phase difference. So they start at the same position, which now just tells us that if I were to add both of them together, then my resultant wave is going to be this huge wave going up and down like this. So that's the beautiful thing about constructive interference. It results in a much larger wave. Now, as the word suggests, constructive, it is making a much larger wave. All right. Now, as it pertains to destructive interference, that one now is when the waves are out of phase with each other, right? Meaning that one is in the positive region, one is in the negative region. When that happens, what we see happening is that the waves are clashing against each other, meaning that this one is positive, this one is negative. We know in mathematics if you have positive 5 and you have negative 5, right? Then it's going to go to 0. So hence the reason why this thing becomes destructive interference, because you have opposites coming together. And once that happens, then it's going to result into being 0. And of course, we say that that's going to be destructive interference. All right. Mind you, for this example, all the waves are on the same height in terms of the amplitude. So as you can see, the amplitude stops here, the amplitude stops here. So this basically makes it a little bit easier as it relates to destructive interference. All right. All right. As it pertains to interference as well, there is um, there are a few things we must talk about, right? We made mention of it a while ago about phase difference, or path difference rather, right? Path difference is just, we should be able to can define it, is that difference in the distance traveled by two waves. So when we look back at, the first wave right here, because both of them are traveling basically from the same position, then there's no difference between them, right? So that's what we call a path difference. So it all depends now on where the wave starts. If one wave starts before another, then there will be a path difference, and you can actually measure the path difference. All right. Now another thing that we must be able to can talk about is what we call a coherent source of light. Now a coherent source of light is one that it produces a set frequency of waves or of light, and also it has a fixed wavelength, right, and also a fixed phase difference. This is going to become very important when we want to deal with the process of interference. In order for us to see interference happening perfectly, you have to use um, a light source that has a set wavelength and also a set frequency, because those things affect interference. If the wavelengths are different and so forth, then it will affect the interference pattern. Now, one of the most useful type of light that you will hear us talking about when we want to use it to perform the, interference patterns is a laser source of light. Now, laser is basically what we call a monochromatic source of light, because it pretty much produces one single wavelength, right? And also it's also a coherent source of light, meaning that it has a set frequency, right? And it also has a constant wavelength and also a constant phase difference. Okay, so it's important that we know about this, and it says that lasers are usually used, right, to perform diffraction experiments as they form clear interference patterns. So if you want to observe interference patterns, you must use a coherent source, and a coherent source is one that has the same frequency and wavelength and also have a fixed phase difference, right? We just talked about interference just now, right? Interference, um, we can perform experiments in the physics labs and so forth to do what do you call it? To basically show that light or wave goes through a process of interference, right? We can do that by using an experiment what we call a Young's double slit. You'll watch another lesson as it pertains to that, which will explain it a little bit more. But essentially, what is happening is that, let's look at it now. In order for diffraction to occur, we know that there has to be a gap, right? And that gap has to be at a certain width so that diffraction patterns can be found. Now, if I were to take two gaps, if I were to take two gaps, let me just draw it right here. So this is one gap in between here, and then I'm going to have another gap right here. Similar, I want to redraw this basically. So when the light comes towards the gap, right, or towards, we call it a diffraction grating for the most part. Whenever the light hits the diffraction grating, you would expect that because it's a gap and the gap has a wavelength that corresponds to the wavelength of the wave, then what you will see is that there are going to be diffraction patterns that essentially are produced, right? Now, mind you that both gaps are going to produce diffraction patterns. So this is what is essentially happening, that you're going to see the patterns overlapping against each other, just like this. You understand? Overlapping with each other, right? When this happens, essentially what we're seeing is that an interference patterns are going to be formed because there are some points when these waves are going to meet constructively, right? And there are also points when they're also going to meet destructively. All right. Now, whenever the waves meet constructively, what we have come to observe on a screen is that there are going to be some patterns that are formed, and these patterns are pretty much showing us that there is interference taking place, right? The pattern looks more like this, to say that you have a very high what you call it now, a very high looking peak thing coming on like that, and you have some smaller thing like this. What this shows us, this portion is showing us that the light, the waves would have met constructively. So the highest peak is talking about when you basically perform a bright fringe. This is what we call the central fringe. You will see it in another lesson. The bright central fringe. There's always a bright central fringe. That is just when these waves would have met constructively. You see what I'm saying? Then no, there are also other points now. So the point where it goes to the lowest point, that is where a dark band, a dark fringe is produced. That is just explaining to us that the wave is meeting destructively. Then clearly you're going to see another bright band or another bright fringe. Wherever you see another bright fringe, it just means that the waves met constructively. All right. So that's a concept we must be mindful of, and it's going to be another lesson. Now we'll talk about reflection in a few.